For most of human history, our solar system was nothing more than a collection of wandering lights against the unchanging stars. Ancient peoples looked up at these celestial wanderers, never knowing that they were worlds unto themselves, some burning hot enough to melt lead, others frozen to temperatures that would shatter steel like glass. A family of worlds bound together by gravity, orbiting a star that has burned steadily for 4.5 billion years. This is our cosmic home, the only neighborhood humanity has ever known. 8 major planets, each a world with its own character and mysteries. Countless moons, some larger than planets, some harboring subsurface oceans that might shelter life. Asteroid belts and distant icy bodies marking the boundaries of the Sun's dominion, all of it held together by the gravitational pull of a star that contains 99.86% of all the mass in the system. What secrets do these worlds hold? How did they form from a cloud of gas and dust 4.5 billion years ago? What can they teach us about the formation of planetary systems across the universe? And which of these worlds might harbor the conditions necessary for life? The answers to these questions reveal not just the story of our solar system, but insights into how planets form, evolve, and die throughout the cosmos. This is the story of our solar system, from the nuclear furnace at its heart to the frozen worlds at its edges. A journey through space and time that begins with a star. September 1st, 1859. Planet Earth is about to have a very bad day. Auroras blaze across the sky, visible as far south as Rome, thousands of miles from where they belong. Telegraph operators around the world watch in horror as their equipment sparks and catches fire. The wires themselves carry deadly electrical currents. Buildings burn. Communication networks collapse. The world descends into technological chaos. This isn't science fiction. This actually happened about 170 years ago. But what was going on? The story begins with Richard Carrington, a British astronomer in his early 30s. He wanted to be a full-time scientist, but had to run the family brewery instead. Fortunately, business was good enough that he could build himself a small private observatory. On August 28, 1859, Carrington noticed something strange. Dark spots were forming on the sun's surface. He documented everything meticulously. The next day, he witnessed something even more remarkable. A bright white flash erupted from the sun's surface, brilliant even against the sun's glare. At first, nothing happened on Earth, but on the following night, all hell broke loose. Instruments measuring Earth's magnetic field went completely haywire. Telegraph networks throughout Europe and North America collapsed entirely. Operators, unlucky enough to be working the machines, received electric shocks. Telegraph lines sparked and set fires. And in places as far south as Rome, Havana, and Hawaii, brilliant auroras lit up the night sky. What Carrington had documented was probably the strongest solar storm in recorded history. We now call it the Carrington event. A massive plasma cloud had detached from the sun, traveled through space, and slammed into Earth with devastating consequences. The sun breathes. It constantly emits particles. A stream of electrons, protons, and alpha particles flows from it. Each particle travels at 400 to 800 kilometers per second, sometimes even faster. Through this solar wind, the sun releases about 1 million tons of matter per second into the universe. For a star like the sun, this is actually a small amount. When solar wind becomes particularly strong in one area for a short time, We call it a solar eruption. A plasma cloud essentially gets shot out like a cannonball. That's exactly what happened in 1859. The bright flash Carrington saw was a side effect of this massive ejection. A solar eruption of this magnitude could still have dire consequences today. Back in the middle of the 19th century, there weren't even telephones yet. If we experienced something comparable today, it would be catastrophic. Satellites would fail, internet infrastructure would collapse, radio communications would cease, GPS systems would malfunction, everything dependent on electrical systems would be affected. The economic impact would be staggering, potentially reaching trillions of dollars. Our best defense is Earth's magnetic field. It deflects most of the solar wind, so charged particles don't hit us directly. Only particularly strong solar winds manage to break through. Against the most powerful eruptions, the magnetic field has no chance. At Earth's poles, some solar particles regularly get through, but that's not particularly bad under normal circumstances. These particles collide with gas molecules in our atmosphere and make them glow. That's how we get auroras, those beautiful curtains of light dancing across polar skies. In 2012, there was another massive solar eruption comparable to the Carrington event, but it narrowly missed Earth. Instead of widespread damage and crashing satellites, there were only brilliant auroras visible much further south than usual. If we hadn't had this incredible luck, estimates suggest up to $2.6 trillion in damage would have occurred in the USA alone. The recovery time for electrical infrastructure could have taken years. So living near an active star like the Sun can be quite dangerous. But what exactly is the Sun anyway? Our Sun is a star, specifically the star closest to us from Earth. In our galaxy, the Milky Way, there are at least 100 billion stars in total, possibly many more. Our Sun isn't even particularly large or small, but quite average. Stars are celestial bodies that emit light and heat through their own power. They can usually do this because they're so massive that they fuse atomic nuclei in their interior. Enormous amounts of energy are released in this process. This is called nuclear fusion. 99.86% of the mass of our entire solar system belongs to the Sun alone. All the rest, Jupiter, Saturn, Earth, Mars, Venus, Mercury, every asteroid, every comet, the International Space Station make up just 0.14%. Because the Sun is so incredibly massive, it has enough gravitational force to keep itself spherical and ensure that all planets and asteroids stay in their orbits. How hot is it really? There's no single answer because it depends on where you measure. The hottest point is the core. Here it gets over 15 million degrees Celsius. The pressure is so immense that atoms are stripped of their electrons and nuclear fusion can take place. On the surface, called the photosphere, it's only about 5,500 degrees Celsius. That's almost 3 times cooler than the center. And then something strange happens. As you move further outward within the Sun's atmosphere, it gets hotter again. In the corona, the outermost region, temperatures reach up to 2 million degrees Celsius. Why is the corona so much hotter than the layers immediately below it? The surprising answer is, we have no idea. This is still one of the great unexplained mysteries of solar physics. Scientists have various theories involving magnetic fields and plasma waves, but nothing has been definitively proven. If you have an idea why this happens, perhaps you could win a Nobel Prize. NASA and other space agencies want to investigate this with the Parker Solar Probe. The Sun is about 5 billion years old. Like other stars in the yellow dwarf category, it has roughly the same amount of time left before it undergoes dramatic changes. When its time is up, it will inflate into a red giant. It will become so large that it will completely engulf Mercury and Venus, and perhaps even Earth. In a grand finale, the Sun will then collapse in on itself. As a white dwarf, it will only shine very faintly for trillions of years. The Sun will not explode in a spectacular supernova. You hear that prediction sometimes, but it's complete nonsense. The Sun is much too small for that kind of death. Only stars with at least 8 times the Sun's mass can go supernova. I often get the question of how the Sun can burn even though there's no oxygen in space. The question is somehow totally justified and makes logical sense. But here's a news flash. The Sun doesn't burn at all, at least not in the chemical sense we're familiar with. Instead, it's a gigantic nuclear reactor operating on a completely different principle. Most of the Sun's mass consists of hydrogen, the simplest and lightest element in the universe. The Sun has so much mass that there's incredibly high pressure inside it, particularly at the core. In the core, it's so hot and the pressure so immense that under these enormous conditions, 2 hydrogen nuclei merge with each other, and boom, they form helium, the second lightest element. This process is called nuclear fusion. The clever part now is that 2 hydrogen nuclei have slightly more mass than 1 helium nucleus. This tiny amount of missing mass doesn't simply disappear into nothing, but is converted into energy, according to Einstein's famous equation E equals mc squared. And we receive this energy as light and heat here on Earth, 93 million miles away. According to this principle, the Sun converts 600 million tons of hydrogen into 596 million tons of helium every single second. That means about 4 million tons of mass are converted into pure energy per second. That's roughly equivalent to 4 billion kilograms transforming into the light and heat that sustains all life on Earth. A little side note here. When it comes to regular nuclear power plants here on Earth, we also talk about nuclear reactors. However, the nuclear reactor in a nuclear power plant works with very large and heavy atoms like uranium. It doesn't fuse them together, but splits their nuclei apart in a process called fission. Energy is also released in this process, with which water is brought to a boil, which turns a turbine that generates electricity. Research is also being conducted on being able to operate nuclear fusion here on Earth, replicating the Sun's power source. But that's incredibly difficult and has been for decades. If that ever works reliably and efficiently, it would be an incredibly good way to sustainably produce massive amounts of energy. With 1 gram of fusion fuel, you could theoretically generate as much energy as is produced by burning 11 tons of hard coal. That is 11 million times more energy from the same amount of raw material, and all without direct carbon dioxide emissions or dangerous long-lived nuclear waste. That's why everyone in the scientific community is extremely excited for the moment when we finally get a successful commercial fusion reactor built and operational. But the whole thing has been an eternal meme of science for generations. For decades, people have been saying fusion power is only 10 years away, and that joke has persisted because it keeps not happening. However, it was not that long ago that, for the very first time in a fusion experiment, more energy was generated than was consumed in the process. That was at the end of 2022 in a laboratory at the National Ignition Facility in California. That was quite a breakthrough moment and represents genuine progress after decades of effort. A manned mission to the sun will never happen. It's much too hot, and there's no solid surface anyway. But there are satellites and probes that explore the sun from a distance. The Parker Solar Probe was launched in 2018. It's currently accelerating as it makes repeated passes near the sun, reaching speeds approaching 700,000 kilometers per hour. It will be the fastest human-made object ever built. Last year, it accomplished something remarkable. It was the first object to actually touch the sun when it flew through the outermost regions of its atmosphere. Temperatures of up to 2 million degrees prevail in the corona. Nevertheless, the plasma is so diffuse that the heat is bearable for the probe with proper protection. The probe will eventually fly as close as 6 million kilometers to the sun's surface. This gives us excellent data and potentially life-saving predictions about future solar storms. Since 2020, another probe has been on mission, the Solar Orbiter, a collaboration between NASA and the European Space Agency. A major goal is to properly photograph the poles of the Sunday. They're surprisingly poorly documented so far. Yes, the sun has a north and south pole, just like Earth. From the poles themselves, there are so far only composite images. The Solar Orbiter aims to provide direct imagery. The sun has been worshipped as a deity by countless cultures throughout human history. The ancient Egyptians had Ra, the sun god who sailed across the sky in a golden boat. The Greeks had Helios, who drove a chariot pulled by fire-breathing horses. The Aztecs had Tonatiuh, who demanded human sacrifices. And it makes sense. People understood that the sun was fundamental to their existence. The sun is the source of essentially all energy on Earth. Without it, Earth would be a frozen, lifeless ball of rock drifting through space. The surface temperature would plummet to minus 270 degrees Celsius. The oceans would freeze solid. Plants use sunlight for photosynthesis, converting light energy into chemical energy. This forms the base of almost all food chains. Herbivores eat plants, carnivores eat herbivores. Without photosynthesis, this entire system would collapse. The sun drives our weather patterns through uneven heating of Earth's surface. The equator receives more direct sunlight than the poles, creating temperature differences that drive winds and ocean currents. The water cycle depends entirely on solar energy evaporating water, which falls as precipitation and flows back to the sea. Even the fossil fuels we burn today are really just stored solar energy from millions of years ago. Ancient plants captured sunlight and grew. When they died, they were buried and transformed into coal, oil, and natural gas over millions of years. When we burn these fuels, we're releasing ancient sunlight, energy captured hundreds of millions of years ago. The more we study the sun, the more we realize how much we still don't know. Why does the solar cycle have the period it does? What triggers solar flares? How exactly does the sun's magnetic field get generated through complex plasma motions? These are questions that the Parker Solar Probe and Solar Orbiter are working to answer. Not far from our sun, we find the first planet, Mercury. It's a world of extremes and mysteries. Mercury is in many ways a puzzle. Although we've known of its existence for thousands of years, it remains the most poorly researched rocky planet. Yet there have been plenty of opportunities to learn more. Mercury is a planet of superlatives. It's the smallest planet in the solar system. It's the one that orbits the Sun the fastest. It records the most extreme temperature fluctuations. And here's something paradoxical. It's actually the closest planet to Earth on average. Spoiler alert, we don't know exactly. Mercury was not discovered by anyone in particular. You can see the planet with the naked eye if you know where and when to look. Mercury was probably first sighted long before there was writing. It was likely observed by prehistoric humans. Mercury is the closest planet to the Sunday. Whenever it can be seen from Earth, it appears very close to the Sun's position. This makes it extremely difficult to observe because the Sun is usually far too bright. That's why you can only see Mercury at sunrise or sunset. It's always found near the Sun, and during the day it's much too bright. It was first mentioned in writing about 2,000 years before Christ by the ancient Sumerians and Babylonians. They called it Nabu, named after their god of wisdom. Among the ancient Greeks, Mercury had two different names. They called it Apollo at sunrise and Hermes at sunset, but they were smart enough to realize it was the same celestial body. It got its current name from the Romans. Mercury is the Roman equivalent of the Greek god Hermes. In Roman mythology, Mercury is the god of merchants, travelers, and thieves. He's depicted with wings on his shoes and helmet because he could move extremely fast, serving as the speedy messenger of the gods. That's exactly why the planet was named after this god, because in our solar system, Mercury is indeed the fastest of all planets. Galileo Galilei and Thomas Harriot were the first people to look at Mercury through a telescope in 1610. Only then did people understand with certainty that Mercury was actually its own planet. Mercury needs 88 Earth days for one orbit around the Sunday. While Earth moves at 30 kilometers per second, Mercury moves at 47 kilometers per second. But a Mercury day lasts much longer than you might expect. Until the year 1965, it was still believed that Mercury was tidally locked to the Sun, meaning that the same side of the planet always faces the Sun, never rotating. That is the same thing that happens with our Moon relative to Earth, which is why we always see the same face of the Moon. But only when Mercury was examined more closely with radar technology in the 1960s did astronomers realize that it does indeed rotate on its own axis after all. For one complete rotation, Mercury needs a full 59 Earth days. So it only rotates 1.5 times on its axis per Mercury year. Those are incredibly slow sunsets and really long lunch breaks. That means Mercury is extremely fast in its orbit around the Sun, but rotates only very, very slowly on its own axis. This unusual relationship between its orbital period and rotational period is due to its proximity to the Sunday. The Sun's gravity pulls so strongly on Mercury that it accelerates it in its orbit, but at the same time has slowed down its rotation on its own axis over billions of years through tidal forces. To figure this out required thousands of years of observations by different civilizations and cultures, and to this day, Mercury holds many surprises for us. Mercury is classified as a rocky planet, just like Venus, Earth, and Mars. And now comes a mind-blowing fact. Mercury is actually the closest of all planets to Earth on average. Venus and Mars are our direct neighbors. How is Mercury closer? The truth is that Mercury is closer to us than Venus or Mars for the majority of the time. Venus and Mars spend much of their time on the opposite side of the Sun from Earth, while Mercury tends to remain relatively near Earth. Researchers demonstrated this with elegant graphics in physics today. For almost half the time, Mercury is actually closer to us than Mars or Venus. And here's the truly crazy thing. This principle doesn't only apply to Earth. Mercury is even the closest planet to Neptune on average, and even to Pluto. Our little grey friend is as fast as the messenger of the gods in mythology. Although Mercury is close to us, it's still the most poorly researched rocky planet. This isn't only due to difficult observation, but also because it's quite difficult to get a spacecraft into orbit around Mercury. Mercury is so close to the Sun that a probe has to fight against enormous gravitational forces just to slow down enough to be captured. It's like trying to park a car while driving downhill toward a massive magnet. And once in orbit, your spacecraft has to deal with truly extreme temperatures. On Mercury's sun-facing side, it can get up to 470 degrees Celsius. On the night side, it can drop to -180 degrees. That means you have to design spacecraft that can cope with temperature differences of up to 650 degrees Celsius. Mercury's atmosphere can hardly store or distribute heat, which contributes to these wild swings. That's why there have only been 2 probes that have successfully studied Mercury up close. Mercury is the smallest planet. Its diameter is about 4,880 kilometers, only a little larger than our moon. There are actually moons elsewhere in our solar system that are larger than Mercury. Saturn's moon, Titan, and Jupiter's moon, Ganymede, are both larger. Nevertheless, Mercury is classified as a planet, and those 2 are moons. Why? Because to be a planet, an object must orbit the Sun directly. Ganymede and Titan orbit other planets. Mercury is quite lonely. It has no moons, no ring system, and not even a substantial atmosphere. Instead, Mercury has what's called an exosphere, an extremely thin shell consisting of sodium, potassium, calcium, and other atoms. This exosphere is created primarily by material that evaporates from the surface due to meteorite impacts. Mercury's surface looks remarkably similar to our Moon's surface. One particular impact crater is absolutely massive, measuring 1,500 kilometers in diameter. It's suspected that Mercury could harbor water ice at its poles in permanently shaded craters that never see sunlight. Nevertheless, it's completely inhospitable for life. The extreme temperature fluctuations and virtually non-existent atmosphere make it utterly uninhabitable. Mercury's surface is almost completely unprotected from dangerous space radiation, since its magnetic field has just about 1% as much strength as Earth's. Mercury's metallic iron core fills an astonishing 85% of the planet's interior volume. That's why Mercury is often called a cannonball by planetary scientists. It's basically a huge iron ball with a thin, rocky coating. The first mission to Mercury was NASA's Mariner 10 probe. It flew past Mercury 3 times in 1974 and 1975, taking approximately 2,700 photographs. The photos showed a very moon-like surface with impact craters, mountain ridges, and chaotic terrain. The mission detected Mercury's weak magnetic field, which was a complete surprise. At the time, no one expected such a small planet to have any magnetic field. Saturn's moon, Titan, and Jupiter's moon, Ganymede, are both larger. Nevertheless, Mercury is classified as a planet, and those two are moons. Why? Because to be a planet, an object must orbit the Sun directly. Ganymede and Titan orbit other planets. Mercury is quite lonely. It has no moons, no ring system, and not even a substantial atmosphere. Instead, Mercury has what's called an exosphere, an extremely thin shell consisting of sodium, potassium, calcium, and other atoms. This exosphere is created primarily by material that evaporates from the surface due to meteorite impacts. Mercury's surface looks remarkably similar to our Moon's surface. One particular impact crater is absolutely massive, measuring 1,500 kilometers in diameter. It's suspected that Mercury could harbor water ice at its poles in permanently shaded craters that never see sunlight. Nevertheless, it's completely inhospitable for life. The extreme temperature fluctuations and virtually non-existent atmosphere make it utterly uninhabitable. Mercury's surface is almost completely unprotected from dangerous space radiation, since its magnetic field has just about 1% as much strength as Earth's. Mercury's metallic iron core fills an astonishing 85% of the planet's interior volume. That's why Mercury is often called a cannonball by planetary scientists. It's basically a huge iron ball with a thin, rocky coating. The first mission to Mercury was NASA's Mariner 10 probe. It flew past Mercury 3 times in 1974 and 1975, taking approximately 2,700 photographs. The photos showed a very moon-like surface with impact craters, mountain ridges, and chaotic terrain. The mission detected Mercury's weak magnetic field, which was a complete surprise. At the time, no one expected such a small planet to have any magnetic field. After that, Mercury remained unvisited for over 30 years. Only in the 1990s did enthusiasm develop again. Researchers began to suspect there could be water ice on Mercury's surface. In 2004, NASA launched the Messenger mission. It took 7 years until the spacecraft could swing into Mercury's orbit in 2011. The spacecraft had to use flybys of Earth once, Venus twice, and Mercury itself 3 times to shed enough velocity. Finally in orbit, Messenger collected data for 4 years. The results included almost 100,000 detailed images of Mercury's entire surface. High concentrations of magnesium and calcium were discovered. A puzzling shift in the magnetic field was identified. Water vapor was discovered in the exosphere, and it was determined that Mercury was volcanically active in its past. In 2015, the mission ended. Messenger had run out of fuel and deliberately crashed into Mercury's surface. In total, it sent over 200,000 photographs back to Earth. Another Mercury mission is already underway. In 2018, the Bepi-Colombo probe started its journey, a collaboration between the European Space Agency and the Japanese space agency JAXA. The goals include investigating why there is water ice in the permanently shadowed craters, why Mercury still has a magnetic field despite its small size, and what are the mysterious hollows on its surface that don't look like typical impact features. These hollows are shallow depressions with bright flaws and appear to be actively forming through some unknown process, possibly related to the sublimation of volatile materials beneath the surface. The Bepi-Colombo mission is actually composed of 2 separate spacecraft that will orbit Mercury independently. The European Space Agency's Mercury Planetary Orbiter will study the surface and internal composition, mapping the planet in multiple wavelengths. The Japanese Aerospace Exploration Agency's Mercury Magnetospheric Orbiter will study the planet's magnetic field and its interaction with the solar wind. Together, they will provide the most comprehensive study of Mercury ever conducted, answering questions that have puzzled scientists for decades. The journey to Mercury is incredibly complex and represents one of the most challenging interplanetary missions ever attempted. You might think getting to Mercury would be easy since it's closer to the Sun, but it's actually one of the most difficult destinations in the entire solar system. Earth is already moving very fast around the Sun, about 30 kilometers per second. To get to Mercury, you need to slow down significantly to drop into a lower orbit, which requires either enormous amounts of fuel or very clever trajectory design. Bepi Colombo uses gravitational assists from Earth, Venus, and Mercury itself to gradually slow down. The spacecraft will fly past Earth once, Venus twice, and Mercury 6 times before finally entering orbit on December 5, 2025. This complex dance through the inner solar system takes 7 years to complete and requires extraordinarily precise navigation. Each flyby must occur at exactly the right time and place, or the entire mission could fail. Scientists are particularly interested in understanding Mercury's unusually large iron core. Why is Mercury's core so much larger relative to its size? Did Mercury once have a thicker rocky mantle that was stripped away by a massive impact? Or did it form closer to the Sun, where heavier elements were more abundant? Understanding Mercury helps us understand how all rocky planets formed, including Earth. Now let's turn to another fascinating world, Venus, Earth's evil twin. Named after the Roman goddess of love and beauty, it's the brightest object in our night sky after the Sun and Moon. Similar to Earth in size, yet absolutely hellish in conditions. Venus transits are rare and historically significant events. They occur in pairs 8 years apart, then not again for over a century. The last transits were in 2004 and 2012. The next won't occur until 2117. In the 18th century, astronomers organized the first international scientific collaboration to observe Venus transits and calculate Earth's distance from the Sunday. This massive effort met with extraordinary bad luck for one astronomer. French astronomer Guillaume Le Gentil traveled to India for the 1761 transit, but war prevented his ship from landing. He waited 8 years for the next transit in 1769. On the morning of that event, conditions were perfect. Then, just as Venus began crossing the Sun, clouds rolled in, blocking his view completely. Nearly a decade wasted. He sailed home, became seriously ill, and arrived to discover his relatives had declared him dead and divided his belongings. If you're having a bad day, remember Guillaume Le Gentil. Despite his misfortune, other astronomers had better luck. Scientists calculated the Earth-Sun distance and narrowed it down to about 152 to 154 million kilometers. That's amazingly accurate for 18th century measurements. The average distance we accept today is about 150 million kilometers, which we call 1 astronomical unit. Venus truly is Earth's twin in some ways. Both planets are nearly identical in size. Both have remarkably similar mass and density. Both likely formed from the same primordial nebula at roughly the same time. Both have iron-nickel cores surrounded by thick mantles of molten rock. Both show evidence of extensive volcanic activity in their past. Both have atmospheres. Both orbit in roughly the same region of the solar system. For these reasons, scientists long wondered if Venus might harbor life. Early science fiction often depicted Venus as a tropical jungle world hidden beneath clouds. But the differences are stark and dramatic. A Venus year takes 225 Earth days, but a Venus day lasts 243 Earth days. A year on Venus is actually shorter than a single day. The planet completes its journey around the Sun before it finishes one rotation. This occurs because Venus rotates incredibly slowly and in the opposite direction from most planets. While Earth spins counterclockwise, Venus spins clockwise. This retrograde rotation is thought to be the result of a massive collision early in the planet's history. The planet barely tilts on its axis, just 3 degrees. This means seasons don't really exist on Venus. Every day is essentially the same. Surface temperatures on Venus reach a scorching 480 degrees Celsius on average, hot enough to melt lead, zinc, and even some aluminum alloys. This temperature is actually hotter than Mercury's surface, despite Venus being almost twice as far from the Sunday. The reason is Venus's incredibly thick atmosphere, which traps heat through an extreme greenhouse effect. The atmospheric pressure at Venus's surface is absolutely crushing, about 92 times Earth's atmospheric pressure. That's equivalent to the pressure you would experience if you dove 1 kilometer deep into Earth's oceans. Any spacecraft landing on Venus would be subjected to this immense crushing force while simultaneously being roasted at nearly 500 degrees. And then there are the clouds. They consist primarily of sulfuric acid. When it rains in the upper atmosphere, it rains concentrated sulfuric acid. The acid evaporates before reaching the surface, but still, the thought is nightmarish. These clouds are so dense that just 3% of sunlight penetrates to reach the surface. Yet Venus shines brilliantly in our night sky because those clouds reflect about 75% of sunlight, making Venus incredibly bright and beautiful from a distance. In addition, Venus's atmosphere is almost entirely carbon dioxide, about 96%. The remaining 4% consists of nitrogen and trace amounts of other gases. This thick blanket of carbon dioxide traps heat so effectively that the temperature difference between day and night on Venus is minimal, despite the planet's incredibly slow rotation. Could life exist in such hell? Surprisingly, perhaps. At higher altitudes, temperatures drop to 30 to 70 degrees Celsius, and pressure becomes Earth-like. Microbes might survive in these relatively mild zones. But Venus wasn't always this way. Billions of years ago, it likely had oceans and an Earth-like atmosphere. As the young sun grew hotter, Venus's oceans evaporated. Water vapor trapped more heat, creating a vicious cycle. Without liquid water, Venus's tectonic plates froze in place. Carbon that would normally be recycled instead escaped into the atmosphere, intensifying the greenhouse effect until Venus became the inferno we see today. Will Earth suffer the same fate? Eventually, yes. As the sun continues aging and brightening, Earth will likely end up like Venus, but not for billions of years. Over 40 spacecraft have visited Venus. Venera 7 landed on the surface in 1970, measuring temperatures of 475 degrees before succumbing to the heat. Currently, Japan's Akatsuki orbiter continues studying the planet. 3 new missions launch in the coming years. NASA's Da Vinci in 2029 will analyze the atmosphere and attempt to land a probe. ESA's Envision orbiter launches around 2030 to study Venus from core to upper atmosphere. NASA's Veritas follows in 2031. Mars, the red planet, humanity's next frontier, the first world beyond Earth where humans will walk. Mars has captivated us for millennia. Ancient Egyptians recorded it 4,000 years ago. The Romans named it after their god of war because of its blood-red color. Its two moons, Phobos and Deimos, mean fear and terror. Recently, Hope, a probe from the United Arab Emirates, captured stunning images of Deimos. The UAE has an active space program doing impressive work. Phobos has only about 50 million years left before it crumbles into a ring or crashes into the planet. Every century, it drifts 2 meters closer to the surface. Mars's distinctive red color comes from rust. The planet's iron-rich rocks have oxidized over billions of years, literally rusting in the thin atmosphere. The planet is about half Earth's diameter, but because Earth has so much water, both worlds have roughly the same land area. Mars boasts the solar system's largest volcano, Olympus Mons, 3 times taller than Mount Everest. The Valles Marineris Canyon system stretches 4,800 kilometers. Why are we so obsessed with Mars? Because it was once habitable. About 3.5 billion years ago, Mars had liquid water on its surface. Ancient river networks, lake beds, and geological evidence suggest possible floods. Rivers carved channels. Lakes filled craters. Perhaps even a northern ocean covered part of the planet. Over time, the atmosphere thinned and cooled, and Mars could no longer hold water on its surface. Why this happened remains unclear. Some think Mars lost its magnetic field, which allowed the solar wind to strip away the atmosphere. Others point to the planet's smaller size and weaker gravity. Some water remains, frozen at the poles beneath the surface. Occasionally, salty water trickles down slopes during the warmest parts of the Martian year. Understanding Mars's climate transformation helps us understand planetary aging. Mars serves as a natural laboratory for studying what happens when a planet loses its atmosphere and water. A Martian day, called a sol, lasts 24.6 hours, remarkably similar to Earth's 24-hour day. This similarity is one of the reasons Mars is considered a good candidate for human colonization. Our circadian rhythms wouldn't need much adjustment. A Martian year takes 687 Earth days, almost twice as long as ours. Mars has genuine seasons because its axial tilt is similar to Earth's, about 25 degrees. During Martian summer, temperatures can occasionally rise above freezing at the equator during midday. During winter, temperatures plummet and carbon dioxide freezes at the poles. Despite these similarities, we absolutely can't breathe the Martian atmosphere. The atmosphere is 95% carbon dioxide, with only trace amounts of nitrogen and argon, and essentially no oxygen. The atmospheric pressure is also less than 1% of Earth's. Without a spacesuit, you'd pass out in about 15 seconds. Your blood wouldn't boil, as movies sometimes show, but you'd definitely die within a couple of minutes. So colonists would have to wear pressurized spacesuits constantly whenever venturing outside, or we would need to terraform the entire planet. Terraforming means fundamentally redesigning Mars so that human life there becomes possible without artificial life support. essentially creating a second Earth from scratch. Whether and how such large-scale terraforming is actually possible is being actively researched by laboratories, universities, and think tanks around the world. The technical challenges are enormous, but not necessarily impossible. We're genuinely on the verge of sending people to Mars within the next couple of decades. This isn't science fiction anymore, it's serious planning and engineering. Initially only temporarily for short exploration missions lasting months or a few years, later perhaps for permanent settlement with families and children born on Mars. NASA officially plans to transport the first astronauts to Mars as early as the 2030s, if technology development and funding continue as planned. SpaceX has even more ambitious timelines, though many experts consider those optimistic. So what would life on Mars look like for these pioneering colonists, and how would we have to modify or change Mars for long-term habitation? First and most critically, you would have to warm up Mars significantly to the point where liquid water becomes possible and stable on the surface instead of immediately freezing or evaporating into the thin atmosphere. Currently, water can only exist as ice or briefly as liquid in special conditions. But how could we warm up an entire planet? Elon Musk controversially suggested dropping thermonuclear bombs on the polar regions to rapidly vaporize frozen carbon dioxide and water ice. The released greenhouse gases could theoretically warm the atmosphere. It sounds like something from a science fiction movie, but he was serious. However, many scientists warn this could backfire catastrophically, creating a nuclear winter instead. Dust could block sunlight for years, cooling Mars further. Moreover, Mars may not have enough trapped carbon dioxide to create a thick atmosphere even if released. Other proposals include deploying massive orbital mirrors to focus sunlight on the polar regions, gradually warming them over decades or centuries. Another idea involves genetically engineered microorganisms designed to produce greenhouse gases, slowly transforming the atmosphere over centuries. Each approach has its own set of problems and would take decades or even centuries to implement. The reality is that terraforming Mars would be one of the most ambitious engineering projects humanity has ever attempted, possibly taking thousands of years to complete fully. 50 spacecraft have been launched toward Mars, making it the most visited planet beyond Earth. Not all were successful. Mars has earned a reputation as a challenging destination. About half of all Mars missions have failed, victims of software glitches, communication errors, or simply the harsh Martian environment. The journey itself is perilous. Taking 6 to 9 months and landing on Mars requires threading the needle between burning up in the thin atmosphere and crashing into the surface. Mariner 4 took the first close-up photos in July 1965, showing a cratered surface that disappointed those hoping for canals or cities. People had imagined ancient Martian civilizations building vast canal networks to transport water from the poles. Instead, they got what appeared to be a dead, cratered world, much like the Moon. The disappointment was palpable, but the scientific value was immense. Currently, 9 active missions operate on Mars or in orbit, representing an unprecedented robotic presence on another world. NASA's Mars Odyssey orbiter has been operating since October 2001, over 2 decades of service, making it one of the longest-serving spacecraft at Mars. It has mapped chemical elements across the Martian surface and serves as a vital communications relay for surface rovers, transmitting their data back to Earth. The orbiter has discovered vast deposits of water ice buried beneath the surface and helped identify the safest landing sites for subsequent missions. Curiosity has been exploring since August 2012, searching for signs of past microbial life in Gale Crater, an ancient lakebed. The car-sized rover has drilled into rocks, analyzed soil samples, and discovered organic molecules that could be the building blocks of life. It famously takes selfies using its robotic arm and plays Happy Birthday to itself each anniversary, a tradition that endears it to the public. The rover has discovered that ancient Mars had conditions suitable for microbial life. It found evidence of an ancient stream where water once flowed, detected complex organic molecules in 3-billion-year-old rocks, and measured seasonal variations in atmospheric methane that could indicate biological activity, though geologic processes could also explain it. Perseverance landed in February 2021 in Jezero Crater, an ancient river delta where sediments might have preserved signs of ancient life. It collects rock samples for eventual return to Earth through a complex multi-mission campaign. These samples might reveal evidence of ancient bacterial life, one of the most groundbreaking potential discoveries in history. The rover also carries an experimental helicopter named Ingenuity that has far exceeded its original 5-flight mission, proving that powered flight is possible in Mars's thin atmosphere. Future missions include Japan's MMX mission to collect samples from Phobos and understand whether it's a captured asteroid or formed from material blasted off Mars by an ancient impact. NASA continues research into atmospheric loss to understand why Mars transformed from a warm, wet world to the cold desert we see today. China's Tianwen-1 mission arrived in 2021 with an orbiter and the Zhurong rover, making China only the second nation to successfully land and operate a rover on Mars. The European Space Agency plans the ExoMars rover, Rosalind Franklin, though launches have been delayed by technical challenges and geopolitical issues. Mars has fascinated humanity for thousands of years. Maybe one day it will become our second home, making us a multi-planetary species for the first time. Another major challenge is the psychological impact of isolation. A Mars mission might last 2 to 3 years, including the journey there, time on the surface, and the return trip. The crew would be hundreds of millions of kilometers from Earth, with communication delays of up to 20 minutes each way. Imagine sending a message and waiting 40 minutes for a response. You can't have a conversation. You can't ask for immediate help if an emergency occurs. If something goes wrong, Earth can't save you. You're completely on your own, millions of miles from any possible rescue. They would need to be completely self-sufficient and work together effectively under stressful conditions. Living in a confined habitat with the same few people for years, millions of miles from home, with no way to escape or go outside without a spacesuit. The nearest reinforcements are at least 6 months away. The psychological toll could be immense. Radiation is another serious concern. Earth's magnetic field and thick atmosphere protect us from most cosmic radiation and solar particle events. Mars has neither adequate protection. Astronauts on Mars would be exposed to radiation levels roughly 100 times higher than on Earth. Over a 2-year mission, the cumulative dose could significantly increase cancer risk. The spacecraft traveling to Mars faces the same problem. In deep space, cosmic rays and solar energetic particles pose constant threats. A major solar storm could deliver a lethal dose of radiation to unprotected astronauts. Shielding helps but adds mass. making the mission more expensive. Some propose using water or fuel as radiation shielding, or even building habitats partially underground on Mars to reduce exposure. It takes a special kind of person to volunteer for such a mission. Brave, certainly, but also deeply curious, adaptable, and willing to accept risks that would terrify most people. The first Mars astronauts will be among the most courageous explorers in human history. Some visionaries talk about making life multiplanetary as an insurance policy. If something catastrophic happens to Earth, having humans living on another world ensures our species survives. It's ambitious, it's expensive, it's dangerous, but it might just be necessary. January 7th, 1610. Galileo Galilei points his improved telescope toward Jupiter and sees something impossible. 3 points of light he can't see with his naked eye hover near the planet. The next night, they've moved. Over several nights, he realizes what he's discovered: moons orbiting Jupiter. The first evidence that not everything in the universe orbits Earth. This discovery triggered one of the greatest scientific revolutions in human history, fundamentally changing how we understand our place in the cosmos. The Earth wasn't the center of everything. Other worlds had their own moons. The universe was far larger and more complex than anyone had imagined. The discovery provided crucial support for the Copernican model of the solar system, which placed the Sun at the center rather than Earth. Galileo's discovery got him into trouble with the Catholic Church, which maintained that Earth was the center of creation. He was eventually tried by the Inquisition and forced to recant his support for the heliocentric model. He spent the last years of his life under house arrest. But his discovery could not be undone. The moons of Jupiter could be seen by anyone with a telescope. The evidence was undeniable. Jupiter, named after the Roman king of gods, is by far the solar system's largest planet. It takes 12 Earth years to complete one orbit around the Sun, but rotates incredibly fast. One complete rotation takes just under 10 hours, the shortest day in our solar system. Jupiter is easily visible to the naked eye, the third brightest object after Venus and our moon. If Earth were the size of a standard globe, Jupiter would be about 4 meters in diameter. Its equatorial diameter is nearly 140,000 kilometers. Jupiter is so massive you could fit all other planets inside it, twice over, with room to spare. Jupiter contains more than twice the mass of all other planets, moons, asteroids, and comets combined. This enormous size means enormous gravitational influence. Jupiter currently has 95 confirmed moons. Most are small captured objects, probably asteroids that wandered too close. But the 4 largest moons, the ones Galileo discovered, are truly planet-sized worlds. The Galilean moons are Io, Europa, Ganymede, and Callisto. Ganymede exceeds Mercury in size and is the largest moon in the entire solar system. It has its own magnetic field, making it unique among moons. Scientists think Ganymede might have multiple layers of ice and subsurface oceans. Io is a world of fire and sulfur, the most volcanically active body in the entire solar system. Its surface is constantly being recycled by volcanic activity, making it one of the youngest surfaces known. Io has hundreds of active volcanoes that shoot sulfur and sulfur dioxide, sometimes hundreds of kilometers high into space. The volcanic plumes can be seen erupting when spacecraft fly past. The largest volcano, Loki Patera, is a lake of molten lava over 200 kilometers across, far larger than any lava lake on Earth. The volcanic activity is so intense that if you watched Io for just a few days, you could see noticeable changes on its surface. This extreme volcanism is caused by tidal heating. Jupiter's gravity squeezes and stretches Io like a stress ball as it orbits, generating enormous amounts of internal heat through friction. Io is caught in a gravitational tug-of-war between Jupiter and the other Galilean moons. This constant flexing generates heat inside Io, the same way bending a wire back and forth makes it hot. But on Io, this happens on a planetary scale, melting rock and driving hundreds of volcanoes. The volcanoes spew sulfur and sulfur dioxide, coating the surface in yellows, reds, and blacks, making it one of the most colorful objects in the solar system. Europa, covered in a thick crust of water ice, likely harbors a vast subsurface ocean containing more water than all of Earth's oceans combined. The ice shell shows cracks, ridges, and chaotic terrain, suggesting the ocean beneath is active and possibly in contact with a rocky seafloor. The surface is remarkably smooth and young, with very few impact craters, indicating that the ice is constantly being refreshed and renewed. Where there's liquid water and chemical energy, there might be life. Europa is one of the best places in our solar system where we could soon discover extraterrestrial life, possibly simple organisms similar to bacteria found in Earth's deep ocean vents. The ocean is kept liquid by tidal heating from Jupiter's gravity, the same process that powers Io's volcanoes, but to a lesser degree. The cracks and ridges on Europa's surface, some stretching thousands of kilometers, suggest that the ice shell flexes and breaks as the moon orbits Jupiter. Some areas show evidence of cryovolcanism, where liquid water or slush has erupted onto the surface and frozen. In 2012, the Hubble Space Telescope detected what appeared to be plumes of water vapor erupting from Europa's south polar region, though subsequent observations have been inconclusive. If these plumes are real and periodic, a spacecraft could fly through them and sample Europa's ocean without even needing to land or drill through the ice. This possibility has excited planetary scientists and has influenced the design of future missions to Europa. Callisto is heavily cratered and ancient, bearing the scars of billions of years of impacts. It may also have a subsurface ocean. The four moons are so bright that if Jupiter weren't there, you could see them with the naked eye. Jupiter also has its own ring system, just like Saturn, but the rings are so faint and made of such fine dust that they're barely visible. They were only discovered when Voyager spacecraft flew past and looked back at Jupiter with the sun behind it. The rings are probably made from dust kicked up by micrometeorite impacts on Jupiter's small inner moons. Now that we know a lot about what orbits Jupiter, let us try to imagine taking a few steps on its surface. Except that's impossible because something quite essential is missing: a surface to stand on. You would just fall endlessly into the planet. Since Jupiter is a gas giant composed primarily of hydrogen and helium with no solid surface, there is literally no ground that could stop you. But let us assume we would not be killed instantly by the intense radiation in Jupiter's magnetosphere and could somehow survive falling into this giant. What would we experience? Let us start a thought experiment, a journey to the center of Jupiter. Our fall begins a few thousand kilometers above the visible cloud tops of the gas giant. Jupiter's gravity is much stronger than on Earth, about 2.5 times as strong, and we would accelerate incredibly fast to terminal velocity. As we do so, we fall faster and faster through several distinct cloud layers, each with its own composition and characteristics. The outermost layer of the atmosphere probably consists of ammonia ice crystals, giving the clouds their white color. Here, there are frosty temperatures of -150 degrees Celsius or colder. Although we could still see the sun from this height, though dimmed by the thin haze, one layer further down, the sunlight reaches us only like on a heavily cloudy day on Earth. This second cloud layer consists of ammonium hydrosulfide, a compound of ammonia and hydrogen sulfide. That is a substance that stinks so absolutely bestially that it is even banned in commercial stink bombs in many countries. Think of the worst rotten egg smell you've ever experienced, then multiply it by 100. In liquid form, it corrodes skin and can damage our eyes forever, causing permanent blindness. Not a pleasant place at all. In the third and deepest cloud layer visible from space, it is now almost completely dark, like being in a cave. But it is getting warmer and warmer as we fall deeper, and the atmospheric pressure continues to rise dramatically. The clouds here probably consist of water droplets and ice crystals, and behave quite similarly to thunderclouds on Earth. They can pile up into enormous cloud mountains reaching hundreds of kilometers high and pour down torrential rain and electrical thunderstorms on us. And because of Jupiter's incredibly rapid rotation, we are additionally whirled around by tornadoes with winds exceeding 500 kilometers per hour, more than strong enough to rip apart any structure humans could build. Below the clouds, we'd fall for hours through hydrogen in various states. The pressure increases until hydrogen reaches a supercritical state, neither quite gas nor liquid. Deeper still, hydrogen becomes metallic, conducting electricity and generating Jupiter's massive magnetic field. At these depths, the pressure is millions of times greater than Earth's atmosphere. We might encounter diamond rain. Some theories suggest diamonds precipitate from carbon compounds deep within Jupiter. Imagine diamonds, some the size of houses, slowly sinking through an ocean of metallic hydrogen. Eventually, we'd reach the core, possibly solid, composed of ice, rock, and metal. The core might be 10 to 20 times more massive than Earth. Jupiter almost became a star. With 13 times more mass, it would have ignited fusion and shine on its own. It would have become a brown dwarf, a failed star, glowing faintly in infrared. Our solar system would have been a binary star system, dramatically different from what we have today. But Jupiter's current size is perfect for us. Without Jupiter, Earth might not support life. Jupiter's enormous gravity deflects or captures asteroids and comets heading toward the inner solar system, protecting the rocky planets. It's like a cosmic vacuum cleaner or a giant goalkeeper, sweeping up debris before it can threaten Earth. Computer simulations suggest that without Jupiter, Earth would experience far more frequent and devastating impacts. In 1994, astronomers around the world watched as the Galileo probe observed comet Shoemaker-Levy 9 crash into Jupiter. The comet had broken into more than 20 fragments, and over the course of a week, each fragment slammed into Jupiter's atmosphere, releasing energy equivalent to 50 million Hiroshima bombs per impact. The impact scars were visible for months, some larger than Earth itself. If that comet had hit Earth instead, it would have been an extinction-level event, potentially wiping out most life on the planet. At the solar system's beginning, Jupiter's role was more complex. While today it protects the inner planets, during the early solar system, it probably directed comets and asteroids toward Earth, delivering water and life's building blocks through countless impacts. The water in Earth's oceans, the carbon in our bodies, much of it probably came from icy bodies hurled inward by Jupiter's gravity. So Jupiter giveth, and Jupiter taketh away. It brought us the ingredients for life, then switched roles to become our protector. Without Jupiter's complex gravitational influence over the history of the solar system, we wouldn't exist. The giant planet has shaped not just the architecture of the solar system, but the possibility of life itself. 9 missions have visited Jupiter. Galileo discovered Europa's subsurface ocean before deliberately crashing into Jupiter in 2003 to avoid contaminating the Moon with Earth bacteria. Since 2016, the Juno probe has studied Jupiter's atmosphere, structure, and magnetosphere. It's revealed stunning details about Jupiter's interior and taken breathtaking images of the poles. In April 2023, the Jupiter Icy Moons Explorer, JUICE, launched. This European Space Agency mission will arrive in 8 years to examine Europa, Callisto, and Ganymede. Saturn, the jewel of our solar system, surrounded by the most spectacular rings imaginable. On its moons, we find clouds, lakes, and seas, perhaps even life. Saturn takes 29.4 Earth years to orbit the Sun but rotates in just 10.7 hours. 9 times wider than Earth with 95 times more mass, Saturn's density is lower than water. If we had a cosmic bathtub large enough, Saturn would float. Like Jupiter, Saturn is a gas giant composed mainly of hydrogen and helium. There's no solid surface to land on. The deeper you go, the higher the pressure and heat. Saturn's ring system is its defining feature. When Galileo first saw the rings in 1610, he thought they were ears on the planet's sides. His telescope wasn't powerful enough to resolve them properly. Christian Huygens correctly identified them as rings in 1655 with a better telescope. The rings are labeled A through G, but not in order from inner to outer. They were named in discovery order: D, C, B, A, F, G, confusing but traditional. The rings consist of billions of particles, from dust grains to mountain-sized boulders, probably remnants of shattered moons and captured comets and asteroids. The ring system extends 280,000 kilometers from the planet, but averages just 1 kilometer thick. If you shrunk Saturn to 1 meter diameter, its rings would be 5,000 times thinner than paper. Why are Saturn's rings arranged on a flat plane? The answer is conservation of angular momentum. When a figure skater pulls in her arms during a spin, she rotates faster. Her angular momentum remains constant, but as mass moves closer to the rotation axis, spin speed increases. Our solar system began as a shapeless, rotating gas cloud. When it collapsed under its own gravity, angular momentum was conserved. Eventually, everything rotating around a common axis flattens into a disk. It's the same reason pizza dough becomes flat when you spin it. Saturn currently has the most moons in the solar system, recently reclaiming first place from Jupiter with the discovery of 62 new moons in June 2023. Most are tiny, but some are worlds in their own right. 2 moons particularly interest scientists: Enceladus and Titan. Enceladus sprays its subsurface ocean into space through geysers at its south pole, where probes have collected samples showing almost all substances necessary for life. The little moon is literally giving us free samples of its ocean. We don't even need to land on it. We just fly through the plumes and collect material. Titan, larger than Mercury, has an atmosphere, rivers, lakes, and seas on its surface. Life might exist there. It's one of the most Earth-like places in the solar system, despite being vastly colder and more alien than anywhere on Earth. 4 missions have successfully studied Saturn. Pioneer 11 arrived in 1979, discovering the F ring and making the first close-up observations of the ringed giant. Voyagers 1 and 2 revealed the complex ring structure in unprecedented detail during their flybys in 1980 and 1981. The images they sent back were stunning, showing details in the rings that had never been imagined, including braided rings, shepherd moons, and intricate wave patterns. The Cassini probe orbited Saturn for 13 years, from 2004 to 2017, providing stunning images and invaluable data before deliberately plunging into Saturn's atmosphere. It was one of the most successful planetary missions ever conducted, revolutionizing our understanding of Saturn, its rings, and its moons. During its mission, Cassini made numerous discoveries. It watched seasonal changes unfold over Saturn's 29-year orbit. It discovered new moons and new rings. It measured the exact length of Saturn's day, which had been surprisingly difficult to determine. It revealed that the rings are far more dynamic than expected, with constant changes driven by gravitational interactions with nearby moons. Cassini discovered geysers erupting from Enceladus, revealing the subsurface ocean. It watched massive storms erupt in Saturn's atmosphere, some large enough to be visible from Earth through amateur telescopes. It flew through the gap between Saturn and its rings during its final orbits, a region never before explored. It was an emotional moment for the mission team when Cassini's end came. After 13 years, the spacecraft had become like a member of the family. Scientists had spent their entire careers working on Cassini. Some had joined the mission as graduate students and were now senior researchers. The spacecraft had been exploring Saturn longer than some team members had been alive. The spacecraft was running low on fuel and couldn't maintain its orbit much longer. Rather than let it crash uncontrolled onto one of Saturn's moons, potentially contaminating them with Earth microbes, the team commanded Cassini to dive into Saturn's atmosphere on September 15, 2017. It sent back data about Saturn's atmosphere, even as it burned up, transmitting information until the very end. The final signal was received at NASA's Deep Space Network, and then Cassini was gone, vaporized in the planet it had studied for so long. The Huygens probe, carried to Saturn by Cassini, landed on Titan in January 2005, analyzing the atmosphere and photographing the surface during its descent and after landing. It revealed a world with rounded boulders made of water ice, sitting in a landscape shaped by liquid methane. The probe operated for about 90 minutes on the surface before its batteries died. But in that brief time, it revolutionized our understanding of Titan. NASA's Dragonfly mission launches in 2027, targeting Titan. This drone-like spacecraft will make short flights over the surface, analyzing the atmosphere for signs of how extraterrestrial life might originate. This represents one of the most ambitious missions ever planned. Titan is one of the most Earth-like places in the solar system, despite being vastly colder and more alien than anywhere on Earth. It's the only moon with a thick atmosphere, actually denser than Earth's atmosphere. The pressure at Titan's surface is about 1.5 times Earth's sea level pressure. The atmosphere is mostly nitrogen, just like Earth's, with about 5% methane. The methane on Titan plays a similar role to water on Earth. It exists as a gas in the atmosphere, forms clouds, falls as rain, collects in lakes and seas, and evaporates back into the atmosphere. Titan has a complete methane cycle analogous to Earth's water cycle. The lakes and seas are filled with liquid methane and ethane, hydrocarbons that are gases at Earth-like temperatures, but liquids in Titan's minus 180 degrees Celsius environment. The largest sea on Titan, Kraken Mare, is larger than the Caspian Sea on Earth. Imagine standing on the shore of an alien ocean filled with liquid methane instead of water, under a thick orange haze instead of a blue sky. Waves lap against shores of water ice as hard as rock in the extreme cold. Methane rain falls occasionally from clouds overhead. It's a bizarre alien world, yet hauntingly similar to Earth in many ways. Titan has weather, seasons, and an active methane cycle. The Cassini mission observed clouds forming and moving, rain falling, and seasonal changes in the distribution of lakes and seas. Near the North Pole, where it's currently summer in Titan's long seasonal cycle, the lakes are more numerous. The South Pole, currently in winter, has fewer surface liquids. The surface of Titan is hidden beneath the thick orange haze, but radar observations from Cassini revealed diverse landscapes. There are mountains, possibly made of water ice. There are vast dune fields of hydrocarbon sand stretching for hundreds of kilometers. There are impact craters, though fewer than expected, suggesting active erosion or resurfacing. There are cryovolcanoes that might erupt water-ammonia mixtures instead of molten rock. Titan is larger than Mercury and has an atmosphere, rivers, lakes, and seas of liquid methane. Beneath the surface, Titan likely has a subsurface ocean of water mixed with ammonia. Could life exist there? The surface is extremely cold, but Titan is rich in organic molecules. Some scientists speculate exotic life forms might use liquid methane instead of water. It sounds like science fiction, but we've learned that life on Earth exists in places we never expected. In boiling hot springs, in acidic lakes, deep underground, in the driest deserts. Life is remarkably adaptable. Maybe it's even more adaptable than we think. NASA's Dragonfly mission launches in 2027. This rotorcraft will fly from place to place on Titan, covering hundreds of kilometers. It will look for organic molecules and signs of prebiotic chemistry that could lead to the origin of life. The mission will take advantage of Titan's thick atmosphere and low gravity. Flying is actually easier on Titan than on Earth. Dragonfly will be able to travel to scientifically interesting sites, take samples, analyze them, and then fly to the next location. It's like having a mobile laboratory that can explore an entire world. Enceladus has geysers near its south pole spraying water ice into space. These plumes contain salt, organic molecules, and molecular hydrogen, suggesting chemical reactions between the ocean and rocky core, possibly at hydrothermal vents similar to those found in Earth's deep oceans. On Earth, similar environments host thriving ecosystems. Deep ocean vents support entire communities of life that don't depend on sunlight. They get their energy from chemicals in the hot water pouring out of the vents, a process called chemosynthesis. Giant tube worms, eyeless shrimp, and strange bacteria thrive in these extreme environments. If the same thing is happening on Enceladus, there might be life there too. The geysers on Enceladus shoot plumes of water ice hundreds of kilometers into space. The Cassini spacecraft flew through these plumes multiple times, analyzing their composition. The discovery of complex organic molecules was particularly exciting. The presence of molecular hydrogen suggests ongoing chemical reactions, possibly providing an energy source for potential life. Future missions could specifically target the plumes looking for biosignatures, chemical evidence of life. We don't even need to land on Enceladus or drill through kilometers of ice. We just need to fly through the plumes with sensitive instruments designed to detect amino acids, complex organic molecules, or other signs of biological processes. It's one of the most promising places in the solar system to search for life, and the Moon is essentially offering us samples of its ocean for free. March 13th, 1781. William Herschel stood in his garden with a homemade telescope and discovered something extraordinary, the first planet found by telescope, Uranus. Herschel initially thought he'd found a comet, but as he and other astronomers observed it, they realized this was something different, a planet beyond Saturn's orbit. The discovery doubled the known size of the solar system overnight. For thousands of years, humanity knew of 5 planets visible to the naked eye. Then in one night, Herschel added a 6th. Herschel wanted to name it after King George of England. European scientists weren't thrilled with that idea. Johann Bode suggested Uranus, the Greek god who fathered Saturn, who fathered Jupiter. It made sense. Saturn's father should come next in the sequence. Uranus is peculiar. Despite being closer to the Sun than Neptune, it's sometimes colder, with extreme temperatures reaching -224 degrees. Unlike other planets that still retain inner heat from formation, Uranus seems to have almost no internal heat left. Uranus is an ice giant. Most of its material exists in a supercritical fluid state, neither quite gas nor liquid. The planet consists of about 80% volatile compounds like water, ammonia, and methane. Methane gives Uranus its blue-green color. The planet has 14 times Earth's mass and measures about 25,000 kilometers in diameter. Uranus has a ring system like Saturn, though much less impressive. Its magnetic field is completely bizarre, rotated 60 degrees from its rotation axis, much stronger on one side than the other, and not centered in the planet. Experts think large oceans of water, ammonia, or even liquid diamond might explain this oddity. Yes, liquid diamond. At extreme temperatures and 40 million times deep-sea pressure, diamond becomes liquid. The most striking feature of Uranus is its axial tilt, 98 degrees, essentially tipped on its side. Earth's 23.5-degree tilt creates our seasons. Uranus's extreme tilt creates extreme seasons. For 1/4 of its 84-year orbit, about 21 years, the Sun beats directly on one pole while the other experiences endless winter. Then, for 21 years, the Sun is over the equator. Then, for 21 years, the other pole gets continuous sunlight. Imagine living through a 21-year winter where the sun never rises, then a brief spring and autumn, then a 21-year summer where the sun never sets. Why is Uranus sideways? Most likely, it collided with an Earth-sized object early in solar system history. This collision could also explain its lost internal heat. All 27 of Uranus's moons share this tilted rotation. They're uniquely named after Shakespeare and Alexander Pope characters. Some orbit prograde, others retrograde. Only one mission has visited Uranus. Voyager 2 flew past in 1986 for just 6 hours. That brief encounter remains our only close-up look. Voyager 2 arrived at Uranus during northern summer solstice, when the North Pole was pointing almost directly at the Sunday. NASA plans the Uranus Orbiter and Probe mission for the early 2030s. China's Tianwen-4 might launch around 2030. The Uranus system is full of mysteries. One of the biggest questions is what happened to cause Uranus's extreme tilt. The leading theory is a collision with an Earth-sized protoplanet early in the solar system's history. But there are complications. If Uranus suffered such a massive impact, we would expect its moons to have orbits that don't align with the planet's equator. Instead, the moons orbit in the same plane as Uranus's equator, suggesting they formed from a debris disk after the tipping event. The peculiar magnetic field also demands explanation. Most planets have magnetic fields roughly aligned with their rotation axes and centered in the planet. But Uranus's magnetic field is tilted 59 degrees from its rotation axis and offset from the center by a third of the planet's radius. This bizarre configuration might tell us something important about how magnetic fields are generated in ice giants. Uranus's moons are named after characters from Shakespeare and Alexander Pope, which is unique in the solar system. The 5 major moons are Miranda, Ariel, Umbriel, Titania, and Oberon. Each has its own fascinating features. Miranda is particularly intriguing. It has some of the most extreme and varied terrain in the solar system. There are massive cliffs called Verona Roops that are up to 20 kilometers high, among the tallest cliffs known. If you fell off the top, it would take you about 10 minutes to hit the bottom in Uranus's weak gravity. There are regions with completely different appearances right next to each other, as if Miranda was taken apart and reassembled incorrectly. Scientists think Miranda might have been shattered by a massive impact and then reassembled under its own gravity. Or perhaps intense tidal heating early in its history caused the surface to partially melt and deform. Whatever the cause, Miranda looks unlike any other object we've observed. Ariel has the brightest and possibly youngest surface of the Uranian moons, with evidence of past geological activity. Umbriel is the darkest, its ancient cratered surface covered in some unknown dark material. Titania is the largest Uranian moon, with a massive canyon system. Oberon is heavily cratered with a mysterious dark floor in some craters. All of these moons might have subsurface oceans. Models suggest that tidal heating and radioactive decay could keep water liquid beneath the icy crusts. If confirmed, this would add 5 more potentially habitable environments to our solar system. The Uranus Orbiter and Probe mission could help determine whether these oceans exist. Uranus and its twin Neptune represent a class of planets that appears to be very common around other stars. Many exoplanets we've discovered are similar in size and composition. By thoroughly studying these ice giants, we can better understand thousands of similar worlds orbiting distant stars. But eventually, inevitably, even red dwarfs exhaust their fuel. The last one will die perhaps 10 to 15 trillion years from now, leaving behind a white dwarf that cools over subsequent trillions of years, fading into darkness. By then, Milky Way will be a graveyard of stellar remnants. White dwarfs, neutron stars from ancient supernova explosions, stellar mass black holes, and brown dwarfs that never ignited fusion will orbit silently in the darkness, cold and dead, monuments to a more active past. Even this remnant population won't last forever in the ultra-long term. Gravitational interactions between orbiting objects lead to energy exchange through close encounters. Close encounters can give one object enough energy to reach escape velocity, flinging it into intergalactic space, while the other loses energy and sinks deeper into the gravitational well, a cosmic redistribution. This process, called evaporation, slowly disperses the galaxy over timescales of 10 to the power of 20 years, roughly 10 billion trillion times the current age of the universe, an incomprehensible duration. Computer simulations show that after this evaporation phase, perhaps 1 to 10% of the galaxy's mass remains in a dense core of tightly bound remnants surrounding the central black hole. The rest has been ejected into intergalactic space, doomed to wander alone through an exponentially expanding cosmos where the space between objects doubles every 10 billion years or so, eternal exile. The peculiar magnetic field also demands explanation. Most planets have magnetic fields roughly aligned with their rotation axes and centered in the planet. But Uranus's magnetic field is tilted 59 degrees from its rotation axis and offset from the center by a third of the planet's radius. This bizarre configuration might tell us something important about how magnetic fields are generated in ice giants. Uranus's moons are named after characters from Shakespeare and Alexander Pope, which is unique in the solar system. The 5 major moons are Miranda, Ariel, Umbriel, Titania, and Oberon. Each has its own fascinating features. Miranda is particularly intriguing. It has some of the most extreme and varied terrain in the solar system. There are massive cliffs called Verona Rupes that are up to 20 kilometers high, among the tallest cliffs known. If you fell off the top, it would take you about 10 minutes to hit the bottom in Uranus's weak gravity. There are regions with completely different appearances right next to each other, as if Miranda was taken apart and reassembled incorrectly. Scientists think Miranda might have been shattered by a massive impact and then reassembled under its own gravity. Or perhaps intense tidal heating early in its history caused the surface to partially melt and deform. Whatever the cause, Miranda looks unlike any other object we've observed. Ariel has the brightest and possibly youngest surface of the Uranian moons, with evidence of past geological activity. Umbriel is the darkest, its ancient cratered surface covered in some unknown dark material. Titania is the largest Uranian moon, with a massive canyon system. Oberon is heavily cratered with a mysterious dark floor in some craters. All of these moons might have subsurface oceans. Models suggest that tidal heating and radioactive decay could keep water liquid beneath the icy crusts. If confirmed, this would add 5 more potentially habitable environments to our solar system. The Uranus Orbiter and Probe mission could help determine whether these oceans exist. Uranus and its twin Neptune represent a class of planets that appears to be very common around other stars. Many exoplanets we've discovered are similar in size and composition. By thoroughly studying these ice giants, we can better understand thousands of similar worlds orbiting distant stars. The planet that was predicted before it was discovered. In the early 19th century, astronomers noticed Uranus wasn't following its predicted orbit. Something was pulling it off course. The deviations were small but measurable. French mathematician Urbain Le Verrier calculated that an undiscovered eighth planet must be causing these perturbations. Using nothing but mathematics and Newton's laws, he predicted exactly where this unknown planet should be. He presented his calculations to the Paris Academy of Sciences. They weren't interested. Le Verrier sent his calculations to Berlin, to Johann Gottfried Galle. On September 23, 1846, Galle searched the sky using Le Verrier's coordinates. They found Neptune just 1 degree from Le Verrier's predicted position. Neptune, the first planet discovered through mathematics rather than observation. It was one of the greatest triumphs of theoretical astronomy. Neptune is so distant, its apparent brightness is 7.8 magnitude, invisible to the naked eye, despite being almost 4 times Earth's size. It orbits 4.5 billion kilometers from the Sun, taking 165 Earth years per orbit. Since its discovery in 1846, it's completed just 1 full revolution. William Lassell discovered Neptune's first moon, Triton, 17 days after the planet's discovery. We now know 14 Neptunian moons. Neptune has 5 main rings named after people involved in its discovery. One Neptune orbit takes 165 years, but one rotation takes just 16 hours. At an average minus 220 degrees Celsius, it's essentially eternal winter. Neptune is the windiest place in the solar system. Frozen methane clouds race at over 2,000 kilometers per hour, nearly double the speed of sound. Imagine winds so powerful they would instantly shred any building, any aircraft, any spacecraft. The atmosphere consists of hydrogen, helium, and methane. Scientists think the blue is partly from methane, but Neptune is bluer than Uranus despite having similar atmospheric composition. Something else must be contributing. Neptune has a solid core about Earth's mass, surrounded by water and molten ice. The Great Dark Spot, a storm similar to Jupiter's Great Red Spot, was first observed in 1989. It has since dissipated, replaced by other storms large enough to contain Earth. These storms appear and disappear over years or decades. We don't know why. It may rain diamonds on Neptune, just like Uranus. At extreme pressure and temperature, hydrocarbon compounds separate and carbon crystallizes into diamond. Deep in Neptune's atmosphere, it might literally rain diamonds. They would form in the upper atmosphere and then sink down through thousands of kilometers. Scientists have replicated these conditions in laboratories and confirmed that diamond formation is possible under Neptune's conditions. Only Voyager 2 has visited Neptune, flying past in 1989. No confirmed future missions exist yet, though China is discussing a nuclear-powered Neptune orbiter. The problem is distance. It takes about 12 years to get there. The spacecraft would need nuclear power because solar panels don't work well that far from the Sunday. Despite these challenges, Neptune is worth exploring. It's the outermost giant planet, representing the edge of the Sun's true dominion. Triton is one of the most fascinating moons in the entire solar system. It's the only large moon in the solar system that orbits its planet in a retrograde direction, meaning it orbits opposite to Neptune's rotation. This immediately tells us that Triton didn't form alongside Neptune but was captured from somewhere else, probably from the Kuiper Belt. Triton is essentially a Pluto-sized object that was caught by Neptune's gravity billions of years ago. When Triton was captured, it would have had a highly elliptical orbit. Over time, tidal forces circularized the orbit, but this process generated enormous heat inside Triton. This tidal heating probably created a subsurface ocean and drove intense geological activity. Even today, billions of years after its capture, Triton still shows signs of activity. Voyager 2 observed nitrogen geysers erupting from Triton's surface, shooting material up to 8 kilometers high. The geysers are thought to be powered by solar heating of nitrogen ice beneath Triton's surface. Even at Neptune's vast distance from the Sun, enough sunlight reaches Triton to drive this geological activity. Triton's surface is relatively young, with strange cantaloupe-like terrain consisting of dimpled, pitted plains unlike anything seen elsewhere. The surface shows evidence of cryovolcanism, where water and ammonia mixtures erupt instead of molten rock. It has a thin nitrogen atmosphere that varies with the seasons and might have a subsurface ocean beneath the ice. Triton's captured origin disrupted any regular moons Neptune once had. The gravitational chaos caused by capturing such a large moon would have scattered or destroyed smaller moons that were already orbiting Neptune. Triton is also slowly spiraling inward due to tidal forces and will either be torn apart by Neptune's gravity or crash into the planet in about 3.6 billion years. When that happens, it will create a spectacular ring system around Neptune, possibly more impressive than Saturn's rings. The debris from Triton's destruction will spread out into a vast ring that could persist for millions of years. The underdog of our solar system. On August 24, 2006, Pluto was demoted from planet to dwarf planet, 76 years after its discovery. How did this happen? What makes a planet a planet? By the late 19th century, we knew 8 planets. Neptune's orbit seemed strange. Astronomers theorized a mysterious planet X was perturbing Neptune's path. Percival Lowell built an observatory in Arizona to find planet X. He searched obsessively but died before finding it. After Lowell's death, the observatory hired Clyde Tombaugh, a self-taught astronomer barely out of his teens. In 1930, the 25-year-old compared photographs and spotted a moving dark object, Planet X. Or so they thought. It turned out that Neptune's orbit was fine all along. The supposed perturbations were measurement errors. But Tombaugh had still found something real. 11-year-old Venetia Burney suggested naming it after Pluto, god of the underworld, a planet named by a child. Pluto is fascinating. It has floating mountains made of water ice, dunes of methane sand, and gigantic ice volcanoes called cryovolcanoes. A thin nitrogen atmosphere exists, expanding and contracting as Pluto moves along its elliptical orbit. Its axis tilts 57 degrees, and like Venus and Uranus, it rotates east to west, opposite to most planets in the solar system. A Pluto day lasts 153 hours, more than 6 Earth days. A year takes 248 Earth years. Since its 1930 discovery, it hasn't completed half an orbit around the Sun day. Pluto is slow, taking nearly 2.5 centuries to complete one journey around our star. At an average minus 232 degrees Celsius, Pluto is far too cold for life as we know it. Any chemical reactions would proceed so slowly that biochemistry as we understand it would be impossible. Water ice is as hard as granite, and nitrogen and methane ices are the mobile, flowing materials. Pluto is small, just under 2,400 kilometers in diameter, smaller than our Moon. It's smaller than 7 moons in our solar system, including our own Moon, the 4 Galilean moons of Jupiter, Saturn's Titan, and Neptune's Triton. Yet for 76 years, it was considered the 9th planet, a status that captured the public imagination. Pluto has 5 moons. Charon is half Pluto's size, so large that Pluto and Charon really form a binary system, orbiting their common center of mass, which lies in the space between them. From Pluto's surface, Charon would appear 7 times larger than our Moon appears from Earth, a massive sphere hanging motionless in the sky since both bodies are tidally locked to each other. The problem wasn't Pluto itself, but Eris, discovered in 2005. Eris is marginally smaller than Pluto, but more massive. If Pluto is a planet, so is Eris, and Ceres. And Make and Haumea. Where do you draw the line? The International Astronomical Union decided to establish what makes a planet a planet. A planet must orbit its star. A planet must be large enough to be round. And a planet must have cleared the area around its orbit. Pluto fulfills the first 2 requirements but fails the third. Pluto exists in the Kuiper belt, surrounded by thousands of objects, therefore not a planet. A new category, dwarf planets, was created. But criticism emerged. Just 5% of astronomers worldwide voted. The third criterion is problematic. Earth and Jupiter haven't completely cleared their orbits either. Some scientists argue the definition is too narrow. According to some proposals, a planet only has to be smaller than a star and round. This would give us over 100 solar system planets. Should we take Pluto back as a planet? The discoverer of Pluto got a happy ending. NASA's New Horizons probe flew past Pluto in 2015, photographing it and collecting data. On board were the ashes of Clyde Tombaugh, who died in 1997, requesting his remains be sent to space. It was a fitting tribute to the man who discovered this distant world. After passing Pluto, the probe will leave the solar system in 2040 and enter interstellar space. Clyde Tombaugh will be the first human to reach that far. His ashes will travel through space long after humanity is gone, a permanent memorial drifting through the cosmos. The New Horizons flyby in July 2015 revealed Pluto is far more geologically active than expected. Instead of a dead frozen world covered in ancient craters, scientists found diverse terrain, mountain ranges of water ice reaching 3 to 4 kilometers high, and active geological processes that continue to reshape the surface. Pluto's famous heart-shaped feature, Tombaugh Regio, named after its discoverer, contains nitrogen ice plains called Sputnik Planitia that show evidence of convection cells, like a lava lamp made of nitrogen ice. The ice is constantly turning over, with warmer ice rising from below and cooler ice sinking. Some regions appear to be less than 10 million years old, incredibly young in geological terms. This was a complete surprise. No one expected such recent geological activity on a world so far from the sun and so cold. The mountains on Pluto are made of water ice, which at these extreme temperatures is as hard as rock and can support tall peaks. Nitrogen ice, being softer and less dense, flows around these mountains like glaciers on Earth. Pluto's atmosphere is mostly nitrogen and extends surprisingly far into space, varying with its orbit. When Pluto is closest to the Sun, More of the surface ice sublimes directly from solid to gas, thickening the atmosphere. When it's farthest from the sun, the atmosphere freezes and falls back to the surface as snow. Charon is tidally locked with Pluto, and Pluto is tidally locked with Charon. They always show the same faces to each other, locked in an eternal dance. Charon has a massive canyon system that dwarfs the Grand Canyon, stretching across much of its surface. It also has a distinctive dark polar cap made of organic material that might have been captured from Pluto's atmosphere or produced by radiation processing of methane ice. Pluto's 4 other tiny moons, Styx, Nix, Hydra, and Kerberos, probably formed from debris when a large object collided with proto-Pluto billions of years ago, creating Charon and scattering smaller fragments that eventually coalesced into these irregular moons. After Pluto, New Horizons flew past Arrokoth in the Kuiper Belt on January 1st, 2019. Arrokoth is 2 objects stuck together, a pristine sample of primordial solar system material. Pluto is one of the largest Kuiper Belt objects. Eris is about the same size. There are probably thousands of objects larger than 100 kilometers across in the Kuiper Belt. The question of whether Pluto is a planet comes down to definitions. The 8 planets dominate their orbital zones. Pluto shares its space with thousands of similar objects. But the debate misses the point. Pluto is fascinating regardless of what we call it. Exploring Pluto was one of the great achievements of the space age. From the nuclear furnace of the Sun to the icy realm of Pluto and beyond, our solar system contains wonders that continue to amaze us. We've journeyed through 8 major planets, encountered dozens of moons, and discovered that our cosmic neighborhood is far more complex and fascinating than ancient astronomers ever imagined. The Sun, our life-giving star, burns through nuclear fusion, converting millions of tons of hydrogen into helium every single second. Mercury, the speedy messenger, races around the Sun while barely rotating on its axis. Venus, Earth's twin, shows us the dangers of a runaway greenhouse effect and reminds us how fragile planetary climates can be. Mars, the red planet, beckons as humanity's next home, perhaps the first step in becoming a multiplanetary species. Jupiter, the giant protector, shields us from devastating asteroid impacts while harboring moons that might support life in their subsurface oceans. Saturn dazzles us with its magnificent rings and mysterious moon Titan, where methane plays the role that water plays on Earth. Uranus spins sideways, knocked over by some ancient collision we're still trying to understand. Neptune, predicted by mathematics before it was ever seen, howls with the fastest winds in the solar system. And Pluto, whether we call it a planet or a dwarf planet, reminds us that science is always evolving, always questioning, always seeking better understanding. The exploration continues, pushing the boundaries of what we thought was possible. Future missions will unlock more secrets. We'll search for life on Europa and Enceladus, diving through the plumes of water ice or drilling through kilometers of ice to reach subsurface oceans where alien life might swim. We'll study Venus to understand Earth's climate future, learning from a world that suffered a runaway greenhouse effect billions of years ago. We'll send humans to Mars, establishing the first permanent settlement beyond Earth and taking our first steps toward becoming an interplanetary civilization. We'll return samples from asteroids and comets, bringing pieces of the early solar system back to Earth for detailed analysis in laboratories. These pristine samples will tell us about the conditions in the solar nebula 4.5 billion years ago. We'll peer deeper into the Kuiper Belt and beyond, exploring the edge of the solar system and the transition to interstellar space. The exploration of our solar system is just beginning. Every mission brings new questions, new mysteries, new wonders. We discover that worlds we thought were dead and frozen are actually geologically active. We find that moons we thought were simple balls of ice actually have vast oceans beneath their surfaces. We learn that the conditions for life might be far more common than we ever imagined. And perhaps most exciting of all, the generation that will answer these questions, that will walk on Mars, that will discover life beyond Earth, that generation is alive today. Some of them might be watching this right now, wondering about distant worlds and dreaming of the day they'll explore them in person. This is our solar system, our home, our future, and we're only just beginning to understand it. The journey continues, and the greatest discoveries may still lie ahead. Future missions will unlock more secrets. We'll search for life on Europa and Enceladus, diving through the plumes of water ice or drilling through kilometers of ice to reach subsurface oceans where alien life might swim. We'll study Venus to understand Earth's climate future, learning from a world that suffered a runaway greenhouse effect billions of years ago. We'll send humans to Mars, establishing the first permanent settlement beyond Earth and taking our first steps toward becoming an interplanetary civilization. We'll return samples from asteroids and comets, bringing pieces of the early solar system back to Earth for detailed analysis in laboratories. These pristine samples will tell us about the conditions in the solar nebula 4.5 billion years ago. We'll peer deeper into the Kuiper Belt and beyond, exploring the edge of the solar system and the transition to interstellar space. The exploration of our solar system is just beginning. Every mission brings new questions, new mysteries, new wonders. We discover that worlds we thought were dead and frozen are actually geologically active. We find that moons we thought were simple balls of ice actually have vast oceans beneath their surfaces. We learn that the conditions for life might be far more common than we ever imagined. And perhaps most exciting of all, the generation that will answer these questions, that will walk on Mars, that will discover life beyond Earth. That generation is alive today. Some of them might be watching this right now, wondering about distant worlds and dreaming of the day they'll explore them in person. This is our solar system, our home,